Let us discuss your assessment. You were asked to derive the least squares estimator of beta in the regression model y I equals xi beta plus epsilon sub I. We can write this down in matrix form by appending the observations row-wise, where xi is a 1 by k vector containing x sub 1, x2 until x sub k. And we assume that x1 is 1, representing the y-intercept. And beta is a column vector containing beta sub 1, beta sub 2, until beta sub k. We can write this equation in matrix form by appending the observations from I equals 1 until n row-wise. So we'll have y1, y2 until y sub n, and that is equal to the matrix containing the vectors x1, x2 until xn times the coefficient vector beta plus epsilon 1, epsilon 2 until epsilon n. In compact form, this is y equals x beta plus epsilon, where x is an n by k matrix. Again here, I is from 1 to n. N is the sample size. To derive the least squares estimator, we want to minimize the sum of squared errors, which is represented by epsilon prime epsilon, which you can write as the summation of epsilon I squared, I from 1 to n. And we're minimizing this with respect to beta, the beta vector. So let's expand epsilon prime epsilon. Epsilon prime epsilon is simply y minus x beta prime y minus x beta. Expanding this equation, we have y prime y minus y prime x beta minus beta prime x prime y plus beta prime x beta. Minimizing epsilon prime epsilon, we get the first derivative with respect to the beta vector, which is equal to 0. And using the properties of your matrix calculus, this is x prime y minus x prime y plus 2 x prime x beta, because this is a quadratic form. And then equating the first derivative to 0, we have x prime x beta, beta hat, equals x prime y. And this implies that beta hat equals x prime x inverse x prime y, requiring the full rank condition for x, which is the rank of x prime x equals k, the number of columns in the x matrix. And this is our equation A4, which we need in deriving the least squares estimator. Now the question is, does beta hat minimize the expression epsilon prime epsilon? Let's find out by doing the second derivative test. We get the second derivative of epsilon prime epsilon with respect to beta. And this is basically 2 x prime x. And since we know that the rank of x prime x is k, therefore x prime x is positive definite. And since the second derivative yields a positive definite matrix, then beta hat indeed minimizes epsilon prime epsilon. And we have solved the least squares estimator beta hat for beta. Now let's check if the least squares estimator beta hat equals x prime x inverse x prime y is unbiased for beta. Getting the expectation of beta hat, we'll have expected value of x prime x inverse x prime y, but now we will replace y by x beta plus epsilon, and this will be equal to expected value of beta plus x prime x inverse x prime epsilon. But beta is our parameter, therefore we will treat it as constant. Now the question is, what's the expected value of this? We have several cases. Case 1, assume that the expected value of epsilon is equal to 0 and that x is non-random or fixed. If that is so, then x is also a constant, giving us the expected value of x prime x inverse x prime epsilon to be x prime x inverse x prime the expected value of epsilon, which is equal to 0. So this thing here will be 0. Case 2 is if the expected value of epsilon conditional to x is equal to 0. For this case, we don't need x to be non-random. And the expression epsilon x prime x inverse x prime epsilon can be written down using the iterated expectations, which is the expected value of the expected value of x prime x inverse x prime epsilon given x. And in the inner layer of expectations, we can factor out x prime x inverse x prime times the expected value of epsilon given x. And since we have assumed that the expected value of epsilon given x is equal to 0, then this expectation is 0. Now the third case is quite complicated because here we assume that the expected value of x prime epsilon is equal to 0, meaning their covariance is equal to 0. There is no correlation or covariance between the variables in x and epsilon. Now for this type of derivation, we need to assume that x is non-random or fixed, so that we can factor out x prime x inverse from the expectation, giving us x prime x inverse times the expectation of x prime epsilon. And based on our assumption, this becomes 0, and the whole expression, the whole thing, is equal to 0. If we don't have this assumption that x is non-random or fixed, then under case 3, beta hat is biased, and the bias has the magnitude expected value of x prime x inverse x prime epsilon. Given the three cases, the expected value of beta hat is equal to beta, meaning beta hat is unbiased for the parameter that it estimates. Now, what's the variance of beta hat? Recall earlier that beta hat can be written in terms of this expression, the thing inside the expectation operator. And beta is just a constant, therefore it will not affect the variance. So basically, we're getting the variance of this expression. And the variance of this expression is just the expected value of x prime x inverse x prime epsilon times the inverse of the expression epsilon prime x prime x inverse. In this case, we need the assumption that x is non-random so that we can factor x out of the expectation operator. So we'll have x prime x inverse x prime expectation of epsilon prime times x prime x inverse. And this simply translates to x prime x inverse x prime times the variance of epsilon, because we assume that the expected value of epsilon is equal to 0. We assume either we have case 1 or case 2. Now this is the form of the heteroscedastic covariance matrix of beta hat. Now if we assume homoscedasticity of the error variance, then we say that the variance of epsilon is equal to sigma squared epsilon times the identity matrix of size n, and this is our assumption A3. And by the way, this is either the assumption A2 or A2, and this is assumption A1 that the model is linear in form. If we have assumption A3, then the variance of epsilon is simply sigma squared epsilon I times n x prime x inverse. We don't have any prime here. And x prime x inverse x prime on this side, giving us the expression sigma squared epsilon inverse sigma squared epsilon x prime x inverse, which is the homoscedastic covariance matrix of beta hat. Now let's use the maximum likelihood estimation. The first assumption that we need, aside from assumption A1, is the assumption that epsilon multivariate normally distributed with mean 0 and variance sigma squared sub epsilon in. Now the PDF of epsilon evaluated at y minus x beta is also the likelihood function, the likelihood of beta given y and x, which is equal to 1 over 2 pi n over 2 times the determinant of sigma squared epsilon I, the variance of the error term, times the exponential of negative 1/2 y minus x beta prime sigma squared epsilon I inverse y minus x beta. And getting the log likelihood function, we have small l of beta given y and then x equal to the expression ln of 2 pi raised to negative n over 2 times the determinant again of sigma squared epsilon in minus negative 1/2 y minus x beta prime sigma squared epsilon I inverse y minus x beta. And we aim to maximize this expression, this log likelihood function. That's why we get the first derivative of the log likelihood function with respect to beta. And this is just negative 1/2 1 over sigma squared epsilon negative x prime times 2 times y minus x beta, which we equate to 0, giving us x prime y minus x prime x beta. And in this case, it's now beta hat after equating it to 0. And notice that we can already solve beta hat, and it is equal to the least squares estimator, x prime x inverse x prime y, assuming that the rank of x prime x is k and invertible. So we still need assumption A4. So to solve for the least squares estimator in MLE, we need the assumption of normality for the error term, which is assumption A5, assumption A4 for x prime x to be invertible, and assumption A1, our assumption of a linear model. You may also check the second derivative of the log likelihood function and see that it is negative definite.